Today I talk about one important topic related to non-linear space. This topic is familiar topics for all. We'll talk about now quotient space. Obviously, one important space. This gives certain fruitful result in mathematics too. So we start about quotient space. Okay. So here we write let X be linear space. X be a linear space. Okay, and y be a subspace, y be a subspace of X. Okay, then what happened? Then for xy belongs to this X, we define what we define in this way: X difference y implies and implies by here X difference y belongs to y. Okay, then what happened? Then this relation is an equivalent relation. We also prove it in previous result, but write this one we write now. Okay, if we want to prove, then you see in previous video. Okay, so we write here in this way: for X belongs to X, and the coset or the equivalence class of X be what? Be this one equal to X plus Y. Here Y belongs to this Y equal to what? X plus capital Y. Okay, then what happens? Then we write here in this way: for xy belongs to this X and alpha belongs to K. Okay, define what? Define box of X plus Y equal to box of X plus box of Y, and alpha box of X equal to what? Box of alpha X. Okay, so what happened? Then X difference, sorry, X quotient Y is difference that then this symbol is needed. Okay, X quotient Y is a vector space, over some field K. Okay, I understand. I think now we erase that portion and going to further discussion of that. We talk about now quotient space, and obviously we see about that quotient space be a vector space. Now we talk about more about in quotient space. So more is what? We write it here: X quotient, X quotient Y. We write difference is not needed here. So X quotient Y be a norm space. We have to prove that. Okay, so we know about that. X quotient Y be a vector space. We also done it. Now we done it. X quotient Y norm space. How this one become a norm space? We talk about in a theorem manner, as a pattern. Okay, so we write this theorem here. Let X norm be a norm space. Okay, now and Y be a closed subspace of X. Okay, not a problem at all. So we're going to forward and further we'll discuss about that. Here this one we've taken one closed subspace, not only just subspace. Okay, so we further talk about define one norm on X quotient Y by norm of X, okay, equal to infimum of norm of X plus Y. Here Y belongs to this capital Y. Okay, and norm of X belongs to X quotient Y. Okay, then what happened? Then x quotient y be a normed space. X quotient y be a normed space. Okay, and this y, how this y is defined, we write in observation. Okay, we write in observation. This one is defined in this way. Oh, we'll not write this one here, but this one is not a problem. Here, infimum of y belongs to y, x plus y. Obviously, we write in this way. Infimum of y belongs to y, x difference y. Okay, so this one in short, t of x capital Y. Okay, that means distance between some point x and some space, close space y. Okay, so we define this norm, and we also now discuss about that x quotient y be norm space. How we discuss this one, how we handle this one, x quotient y be a norm space. We erase our portion and going to further discussion of that. Okay, so we write it now. First result, norm x, here x quotient y equal to greater than equal to 0 if and only, and this one we have to prove, and here norm of x quotient y equal to 0 if and only if x equal to 0. Okay, here this 0 obviously in x quotient y. So what happened? By definition, we write it in this way. By definition of x quotient y, we get what we get here, norm of x quotient y greater than equal to 0 for all norm x belongs to x quotient y. Okay, then what happened? Then let x belongs to x, and we now show that what we now show that this norm x equal to 0, okay, implies by here x equal to 0, this one. Okay, this one means y. So we show this one. So how we do this? We write here again. Suppose that okay, suppose that this one equal to 0, then this implies what? This implies infimum of y belongs to y. Okay, x plus y equal to 0. Then this implies what? Then there exists a sequence. Y in y such that limit n tending to infinity norm of x plus y n equal to 0. Okay, this implies that x plus y n equal to 0 as n tending to infinity. Okay, This implies that what y in converge to minus x as n tending to infinity. Okay, so what happened? Again we erase our portion and going to further discussion of that. We write here now, since y be closed, so what happened? Then obviously minus x belongs to y. So what happened? This implies that x belongs to y. So what happened? We write thus box x equal to x plus y. Obviously y, because this x belongs to this y. I understand or not? Understand? So we do it. That means this gives, okay, this gives us this one, x equal to 0, this one. Okay, so we now erase lower portion and going to later part of this proof. Okay, so later part is what? Later part we write it now conversely. Conversely, suppose that box x equal to 0, x difference y equal to y. Then we have to show that this box x difference y equal to 0. Okay, sorry, this one we have to show that norm of this one equal to 0. Okay, norm of this one equal to 0. So what happened? What we write here? We write in this way, this x equal to y. This implies that x belongs to y. Okay, again this implies that x plus y belongs to y when y belongs to y. Okay, so this implies that infimum of y belongs to y, here x plus y equal to 0, and this implies norm of x quotient with respect to x quotient y equal to 0. Okay, then what happened? Then we erase that portion and going to further discussion of that. Here we write n2. Okay, then what we have to prove now? Then we have to show that norm of alpha box of x, okay, x quotient y equal to mod of alpha, here norm of x quotient y. Now for alpha equal to 0, what happened? This equality hold. Okay, let alpha not equal to 0. Then what happened? Then norm of alpha box x difference y equal to norm of alpha x difference y equal to infimum of alpha x plus y. Sorry, okay, we write in this way. No, not needed here. Okay, this one y and y belongs to this y. So we write again infimum of alpha is common, then alpha outside this norm and x plus y 1 by alpha norm. Okay, then what happened? We write it now in this way infimum of, here y belongs to y belongs to y, then we not write here, we write u belongs to y norm of x plus u. Here here alpha is in outside. Okay, and here we write what, u equal to alpha 1y belongs to y. Okay, then what happened, then this equal to alpha nor box x quotient y. Okay, so done. Now we're going to proof of triangle inequality. Okay, this one obviously one important topics related to quotient space. First we defined quotient space and then we prove this quotient space be a norm space. We also first discuss greater than non-negativity part, and obviously equal to 0 implies this equal to y or 0 in with respect to norm quotient space. And obviously then we discuss about this homogeneous part, and now going to triangle inequality. We erase that portion and going to further discussion of that. Okay, so we going to part triangle inequality. We know about that triangle inequality, one important inequality. Okay, so we now discuss this one, this triangle inequality. Here we write let xy belongs to x. Then what happened? Then we know about that this one. Okay, x quotient y equal to what, infimum of box of x plus u. Here u belongs to y, and here norm of y, here x quotient y equal to infimum of v belongs to y, here norm of y plus v. Then there exists un and vn in y such that limit n tending to infinity box norm of x un equal to box x quotient y and limit n tending to infinity norm of y bn equal to box y x quotient y. Okay, so what happened, here we write this one now, quotient x plus y box x box y with respect to this quotient space equal to what, equal to, we write it now, infimum of z belongs to y, here mod of x plus y plus z. Okay, and this implies quotient of x quotient y less than equal to mod of x plus y plus z. Okay, for all z belongs to y. Okay, now we erase our portion and going to further discussion of that. Okay, so we're going to step by step manner, and where we arrive we write it now. Note that un plus vn belongs to y. Okay, for all n belongs to this natural number, it follows that norm box x box y x y less than equal to x plus y plus un plus vn less than equal to x plus un plus y plus vn for all n belongs to this natural number. And now taking limit as n tending to infinity, we get, okay, this one equal to box x quotient y, this one equal to box y x quotient y. Okay, so we also going to proof of that. What proof? We write it now here. This one, box x plus box y. Okay, oh, this one we write it in this way. Okay, box of x plus y. This one is better or not? I think better, or in this way. Okay, this way is better, not here, this one. Okay, so we write in this way, box x plus box y here less than equal to norm box x and box y. Okay, so we arrive this portion. So what we today learn, we known about that quotient space, and obviously quotient space become noun space when y be closed. Y closed is necessary. This one y be closed subspace, this one is necessary for that proof. Okay, so this one obviously that means needed. Now if we get this type of videos, then obviously subscribe my channel, and if you like this video, so gives like, and if you have any questions, please write it in comment box, and also obviously that means gives you some solution. Okay, so today I stop here.